Okay, so this problem we want to compute the level of service through an intersection. You'll notice a couple things about this before we read the given stuff. We have stop signs coming in from the southbound. The northbound has a stop sign as well. The east and westbound traffic are uncontrolled. There is no stop sign there. We do on either side, and there's no signals. We do have crosswalks on all of the roadways. If we take this four-direction thing and replot it, I can give you what the flow rate is, first number here, and the movement number. Remember, we have to keep track of movements when we analyze this thing. Okay, so we have the movement number, the flow rate, and right here I tell you what the pedestrian movement is. This is the flow rate for pedestrians, and this is the movement number. So this crosswalk here is represented by this vector down here, and it is showing a pedestrian flow rate of 30, and it is movement number 16 for reference purposes in our problem. This particular crosswalk is this vector, and it has a flow rate of 15, and it is movement number 14. What about vehicular traffic that's over here, vehicle movement? So we have coming in from northbound, going northbound, we seem to have a movement number 9, movement number 8 is straight through, and movement number 7 is a left turn movement. Okay, we have the flow rates in front, and so here's the westbound and here's the eastbound. Okay, so for our example here, they are telling us that for this two-way stop controlled intersection, find the potential capacities for movement 7, find the movement capacities for movement 7, find the control delay and level of service for movement 7. Movement 7 is right here. You'll notice that I've labeled it in magenta number 7, so that's the one we're interested in. The others on the page are in blue. That's information. Let's go back to the givens here. We get to use the speed of pedestrians is 1.2 meters per second. All flows contain 8% trucks. We have a flat roadway grade, and we can ignore southbound turn movement. So up here, you may have been wondering, just looking at this thing, I seem to have northbound bunch of movements, westbound movements, eastbound movements, but I seem to have nothing from the north, which would be this roadway here. That's because we are ignoring this for this particular problem. Ignore southbound turn movements. Okay. So we have three things we have to go figure out. Let's go work with our tools, see how we can do this. So the first thing we're going to do is come up with the critical gap and follow-up time. We're going to be using the highway capacity manual tables. The critical gap is it's called the T sub Cx. So we're going to take the T sub Cb plus the T sub Chv times the peak hour factor plus the T sub Cg times two other factors. So we have to go find all these things. We have to go find all these things. So the first thing we're going to look for is we understand that we have from the problem statement it is 2-lane, not 4-lane. We're going to look for the 2-lane. And the movement we want is number 7, which is left turn, and it's from the minor of the two sets of roads. The major roads are east-west. The minor, because they've got the stop signs on them, and our subordinate, are the north and south. So the northbound left turn movement is the one we're interested in. That's number 7. And so the left turn from a minor on a 2-lane roadway is 7.1. 7.1. So we're going to hang on to that. The adjustment values are down here for the equation. We've talked about what each of these are. Movements number 7 is identified here, so we're going to use a T sub Cg of 0.2. We're looking at a one-stage process, so we get 0 for the T sub 3 LT. And then the heavy vehicle factor it's 2-lane, 4-lane, we're going to go with otherwise, okay? Because it is not a major streets that we're looking at. So, from those tables then, we have our values printed out down here. We can jam them into, for movement 7, we can jam them in down here, and we come up with a 7.18 seconds is what we're after for the critical value. Again, what is this thing? If we go back up to the top here, we are looking at the critical gap. Next thing we need to do is to compute the follow-up time. Again, we have a base T sub FB of, we look it up in our table, it's right here, corresponds left turn from a minor because that's our movement number 7. This is the value of our base. We then have our adjustment factors against it, and that's what we get in the table that we were looking at earlier. So here we are with the heavy vehicle right here. 2-lane is what we're going on to. It's 0.9. And so from these two tables, we can now compute that. We got the values here from the two tables. We can now compute. Okay, at movement 7, we can compute how many seconds. It's about 3.6. Now what we can do is compute the conflicting flow rate. What we're doing is we're taking each of the flow rates after we've identified the conflicting movements. Now, we already computed or already identified which movements are conflicting against our movement number 7. It's movement number 1, 4, 5, 13, 2, 3, and 15. If we were to go back to our drawing and find those, we would see that in fact these things conflict with our left turn movement number 7, and these we have to worry about in terms of they create they conflict with our movement. So what is the conflicting movement in aggregate? We have to add the volumes up for each of those, but you'll notice that there's multipliers of 2 on some of them, a half on others, and simply 1 on the remainder. We discussed this earlier as to which factors belong where. Okay, so we're simply applying that here. So if I put my values in, I wind up with a conflicting against left turn movement 7 of 760 conflicts per hour. Now I need this value to continue on with this rather complex computation. So now I can figure out my potential capacity. We have here the standard equation from the Highway Capacity Manual, but we have just figured out the pieces that we need. Here is the 760, here is the 7.18, and here is the 3.59. The 3600 is how many seconds in an hour. The terms in the numerator in each of these exponents happens to be per hour. Okay, so that we're converting that over. So now we wind up then with our value of potential capacity for movement number 7, that's what C sub P7 is 312 vehicles per hour. That's the potential capacity. Okay. Okay, so that's our potential capacity. Now I have to figure out what's going to eat away at that potential capacity, and it's going to be the impedance. What vehicles impede the flow number 7 here? So from this figure, which things impede that? It's going to be, just looking at it, movement number 4 and 1, and that's vehicular movement. And then we have a pedestrian couple of movements, 13 and 15. I point those out down here in yellow. Which ones are impeding? Which ones are impeding? These are the vehicle ones, and these are the pedestrian ones. Which ones are impeding number 7? Once we've identified those, we can then come up with what the probability of impedance is going to be. We pull up our main equation here, so let me highlight that. I know this is complicated and confusing, but that's just the nature of this beast. I have boiled this thing down best I can. Okay, so our pedestrian impedance probability, our main equation, general equation, is there highlighted. I'm going to poke in, you'll notice, my pedestrian flow rates that were given to me for movement 13 and movement 15. These are for pedestrian pieces. Okay, so I had the 15 in one direction, 30 in the other. Where is that, you might ask? Let's go find it. The 15 and the 30. Here they are. 15 right there and the 30 right there. 15 belongs to movement 13. 30 belongs to 15. We're going to do the same thing. Oh, anyway, I don't want to get ahead of myself. So I've got those pieces, got the lane width that was given to me. I'm going to use half of it, half of the total roadway for my lane width. Here's the other lane width for its movement. Okay, they already told me what these are in the problem statement. And then the pedestrian speed, they gave that to me as well. Okay. Now when I say they gave me these, they're actually on the drawing. This pedestrian speed was given to me explicitly. Okay. So I'm able to come up with these two values here of the pedestrian impedance probability for the two conflicting movements that I identified pedestrian-wise anyways. Now we have to do the very same thing on vehicular, except we have to use a different equation for this one. Okay, so here's our general equation. I'll go ahead and highlight that to stay consistent here. And I poke in my values. I've already computed these things, so I get the vehicular impedance probability against movement number 4, vehicular movement number 4, as 0.935. Once I have that, my goodness, once I have that now, I can go to the moment capacity, or movement capacity, I should say. I'm sorry, this is a typo. This should be movement capacity. Here's my equation down here. This is the general form of it. This is what it is for us with the movements identified. Now remember, we're looking for impedance, so I just have the values in there for things that are impeding progress of movement number 7. So I put in my values and I come up with 271 vehicles per hour are impeding my left turn movement at movement number 7. So now, are we having fun yet? So now we can finally calculate what we're bothering, which is the delay. What is the control delay for movement number 7? The main big equation, general, is right here. We have everything, believe it or not. All the stuff that we've just tried to come up with, we finally have everything. We populate it down below here, and we get 23.24 seconds per vehicle is our control delay. We can now take that finally and enter our level of service, 23.24. We find it, and we have a level of service of C.